So today we're introducing the idea of inverses. Some of them will be inverse functions. That's a way that it's often described as inverse functions. But inverses can be of any relation. They don't even have to start as a function. So take a look at what we have here. We're told here that the inverse of a relation is found by swapping the x and y values. That is the most fundamental concept behind the inverse that there is. And you're going to find that everything else we do is basically some sort of a variation on that same theme of swapping the x and y's. Now, we're going to start with a hopefully fairly straightforward example here. We're going to be looking at this table of f of x that we have. So we start with this table over here. And what we're going to do is we're going to make a table for the inverse, which notice how it's written here. It looks like f to the power of negative 1 of x. And yes, that's how you would write it. It's like it's an exponent saying f to the power of negative 1. But that's not how we read it. We read it as the inverse of f of x. So that's one of the first things we're getting down today is that correlation. How do we read it and how do we write it? Now, we are going to need to actually make this table. Well, the whole idea of the inverse, remember, is swapping the x and y values. So if I'm going to make a table of the inverse, I'm going to take each of the values in the original table over here, and I'm going to swap the x and the y's. So my first point in my inverse table, it's going to be at 6, negative 4, because I'm swapping the x and y coordinates. Straightforward, I hope. Go ahead and finish making that table. All right, and so as I go down and fill in the rest of this table, all I'm doing is switching the x and y values. So negative 2, 0 becomes 0, negative 2. And we just keep switching those x's and y's to see what our new points are going to be. Now, in this particular case, I'm just given the points of the function. But I can take those points and plot them and kind of get an idea about what this function might look like. So on your first graphing grid, let's plot the points of f of x. Now, I suggest that you do this in two different colors. I suggest you use one color for f of x and one color for the inverse of f of x. But if you don't have different colors, at least be labeling each one. All right, so find the points of f of x. I go to negative 4, 6, and plot each of the other points in there. Then having plotted each of those points, we can see we end up with a shape that actually seems somewhat familiar. It actually is going to happen to be a parabola shape. Now, we wouldn't know that based on the information given, but I'm telling you that, yeah, these are points that are part of a parabola. So I'm going to have you draw in the curve here just so that we can have a better visualization about what's going on between the original and the inverse going forward. So there's our f of x graph. Plot the points. Go ahead and draw a parabola through them. Then next up, on the same set of axes, we are going to graph the inverse of f of x. I'm going to be doing it in red. Now, if you don't have separate colors, you'll want to label each of the graphs with the function name. So the first one would be f of x. All right, so now we just go through and again, plot each of the points for the inverse of f of x, just like we did for the first one. And then, again, I want to draw in the curve that seems like it goes through it. In this case, the curve is still basically a parabola shape, but in this case, it's on its side. So draw on that curve, and again, either have it labeled with the right colors, or at least label it with the name. So we got f of x, and we graphed the inverse of f of x. Make sure that everything is plotted as accurately as you can. You're going to find that we're going to be coming back to this graph in a little bit here to use it as a reference to see some other stuff that we are doing. All right, now having these graphs down, we will be referencing them, but before we go and look at some of the details about how these are related, we're going to be actually also looking at the equations In this case, we didn't start with the equation. We just started with the points. So what if I did start you with an equation? This actually goes into your notes. To find the inverse equation, we swap the x and y. Notice a theme there. The very first thing we learned about the inverse is it swaps x and y. But then in order to find the inverse equation, after we swap the x and y, we'll solve for y. Now we'll do an example of this in a moment, but first get it written down to your notes. So to practice that idea of finding the inverse equation, we're going to find the inverse of this equation. Y equals x squared plus 1. So start on your own paper, write down this equation, and then we'll actually walk through the process described by those short notes that you just took down. All right, so step 1, remember, of finding the inverse equation, was to swap x and y. Now when we swap x and y, we're only swapping the letters. Anything associated with those letters stays exactly where it was. So the y becomes an x, the x squared becomes a y squared. So literally, the only thing we just changed was just swapping the x and y. Part 2 of our notes said solve for y. So now we need to solve this equation to make it into y equals instead. Because while this is the inverse equation, it's not actually been solved out. And we do want to be a y equal, so that it's actually something we can work with. All right, so if I'm going to solve this for y, what do I need to do first? Yep, we want to subtract that 1 from both sides. Because when solving a squared equation, a quadratic like this, we want to get the quadratic by itself. Oops. So now I have x minus 1 equals y squared. Now I can worry about getting rid of the squared. Okay, so what undoes a squared? Square root. So I'm now going to take the square root of both sides. Now when I do that, on the left side, that gives me the square root of x minus 1. And on the right side, the square root of y squared, I do the square root because it cancels out the squared. So it just equals y. Now there's one thing that we have to remember when taking the square root that I have not yet written in here. What is it? What do we have to include when we take the square root of both sides of an equation? Yep. Plus or minus. Put that plus or minus in front of that square root when you take the square root of both sides. That is going to be important here because if you don't include that plus or minus, it's not actually the inverse. It's actually only going to be half of it. And we'll actually see an example of how that looks on the graph here in a moment. But first, make sure you have the equation written down correctly. All right, so now we're going to take a look at the graphing side of it. So we found the inverse equation. We got that. We're now going to graph both of these on the same set of axes. So on the second set of axes that you made, please start by graphing y equals x squared plus 1. Again, having 2 different colors for each of the graphs as we make them will be helpful. All right, so when we make the graph of y equals x squared plus 1, the plus 1 moves it up 1, and from there it's a x squared graph like normal. So over 1 up 1, over 2 up 4, and over 3 up 9 on both sides. This one definitely is a parabola because we have the whole equation. Draw the parabola curve through those points. And then we go to actually graph the second, the y equals plus or minus square root of x minus 1. Now when you go to make this graph, right now you might be thrown off by the plus or minus, because we haven't necessarily graphed something that has that in it before. So in order to make this graph, step 1, ignore the plus or minus for the moment. So start by just graphing y equals root x minus 1. And then we will go put that plus or minus back in there afterwards to see how to handle it. And so in graphing root x minus 1, the minus 1 moves at right 1, so you put your first point right 1. And then we'll make our standard square root graph from there. So square root of 1 is 1, so I go over 1 up 1. I don't want to go over 2 because I don't know the square root of 2, or at least if I do, it's a decimal and not a nice pretty number. Instead, I want to go over 4 because I know the square root of 4 is 2. So it's over 4 up 2. Then the next number I can take the square root of nicely is 9. So square root of 9 is 3. So that's what the second graph would look like. The inverse graph would look like without the plus or minus in front. But unfortunately, I do have to account for that plus or minus when making the graph. So what do we do with the plus or minus? Well, just like when we're doing algebra and there's a plus or minus in there, it means do it once with plus and once with minus. Same thing here. It means graph it once where we graph positive root x minus 1. And it means graph it once where you do negative root x minus 1. So I'm going to graph y equals negative root x minus 1 now, along with the positive one that I just drew in. What's the negative out front do? It flips it upside down. So, for instance, instead of over 1 up 1, I go over 1 down 1. Fill in the rest of those points.
Can we connect it on that side?
And then once you've drawn in those points, we draw on the curve. And the curve is just like it was the first time, the top half we drew, except that it's going down instead of going up. So now, notice how the graphs compare here. There's going to be some things that we're going to get into, but start thinking through. How do these graphs compare? What's the same about them? What's different about them? And we're going to start investigating that. To start taking a look at these, we're going to start by answering these questions of, are both of them functions first? Now, let's start with just the original, the y equals x squared plus 1, our blue graph in this case. Is that a function? Well, if you're not sure, remember how we tell. Remember the vertical line test? I should be able to draw a vertical line through that graph anywhere and never hit it in more than one point. That means it is a function. So, is the original here a function? Yeah. So the original, that is a function. What about the inverse? Is the inverse a function here? Well, that point, for example, notice my vertical line is hitting it more than once. So that means no, it's not a function. So while the first one is, the second one is not a function. So even if you start with a function, it doesn't mean that your result, your inverse, will be a function. Now, sometimes it will though. So it doesn't mean that the answer would always be no. Sometimes the answer would be yes here, but it depends on what you started with. All right, now let's take a look at domain and range and how those relate. So for the original, the domain. First of all, does domain deal with x or y? X, yeah. Domain is the possible x values. Well, as we look at our original here, as I go to the left, do I ever run out of graph? Of course, it's off the graphing grid. I can see that, but that's okay if it's off the graphing grid. Can I ever go left far enough where there's no more graph? No. No matter how far over to the left I go, I could go to a negative million. I'd have to go up a long ways, but I would eventually go up and hit graph. What about if we headed to the right? Do I ever run out of graph heading to the right side? No, I don't. So then, what do we call a domain then that includes everything? All real numbers, yeah. So my domain for my original is all real numbers. Okay, what about the range then? Does range deal with x or y? Y, absolutely. And so I'm looking at the possible y values on my blue graph, my original graph. So for this one, I'll tell you right now, it's not all real numbers. Because notice this graph, it only goes down to here. Our graph is all of the y values that are above that line. So, how do I write it? Well, it's all the y values. It's everything above, so it's got to be greater than or equal to. And what are they all bigger than? 1. So our range, y is greater than or equal to 1. Now it's time for our inverse. So now we're looking at the purple graph, the one opening towards the right there. The domain, is the domain for our inverse all real numbers? No. Because, notice again, I can think of it as, well, it's starting over here, and then it's heading to the right from there. So it has a limit. It only goes left that far. Okay, so then my inverse domain, x is going to be what? Greater than or less than? Yep, greater than or equal to, because it actually hits it. And that line, that starting point, the lowest x it reaches, is 1. So our inverse domain, x is greater than or equal to 1.
Wait, so then why wouldn't the domain...
All right, so now the range, though, the range of the inverse, is the range of the inverse all real numbers? Well, we're looking at y values here because it's range. Does it go up forever? Does it go down forever? Yes, on both counts. It might have to go a long ways to the right, but it does go up and down forever. So our range of our inverse is all real numbers. Do you notice any pattern here between the domain and range of our original and our inverse? Yeah, it's just switched, right? Think about this. For instance, let's take a look at the original range and our new inverse domain. Remember what the inverse does. The inverse swaps x and y, right? Well, range talks about y, domain talks about x, so I'm just swapping which one's talking about what basically here. So our old range becomes our new domain. But of course, since I'm switching them, I'm switching the fact that the original was y for our range, and our new domain has to do with x, so I do have to call it x or y appropriately. Same thing happens with the original domain and the inverse range. Notice they're the same. It's just the original domain is saying that all the x's are all the real numbers, and the inverse range is saying that all the y's are all real numbers. All right, so there's a lot of little detail in there. We got to get some of this information formalized into notes. So add all of this information into your notes now. All right, so the information up here, a little bit more depth on some of these. First, it may or may not be a function. We saw that. We saw in one case the inverse was not a function. There certainly will be cases where it also is a function, though. The most fundamental idea of the inverse, of course, is this second bullet, that it switches all the y and x values. Everything swaps. So if I have a point, the x and y swaps. If I have an equation, I swap the x and y, etc. The graph is reflected across the line y equals x. Now this one we haven't seen yet, so we're going to take a quick look at that and then come back to some of this. So here's the graphs that we made in that last problem, but you notice that dotted line there? That dotted line is the line y equals x. Now, somebody always ends up scrunching their forehead at that. Why is that y equals x? Notice we got a y-intercept of 0 and a slope of 1. So it started 0, up 1 over 1, etc. So this is the inverse because you'll notice that every point of the original has actually been flipped directly across that dotted line. In fact, there will be times when we'll have to find inverses, and we may not know how to actually graph the inverse function. And in order to make the graph, you'll actually start by just taking each of the original points that you made up here and flipping them across that line. So there's a hint going forward that if you find that you cannot make one just from the graph, you can take your original graph and flip the points from that. Now, going back to that very first graph that we made, you can also see it in this one. If I were to draw in the line y equals x here, you'll notice they were flipping across that as well. A few things to note in particular on that. You notice this point right here. If one of them hits that line, y equals x, they'll both hit that line, y equals x. So if one hits that line, they'll both hit it at that same point. Because, of course, if you reflect a point onto itself, it's in the same place. That would actually happen down here as well, if I drew in every little detail of that graph accurately. And you can also see other individual points getting flipped across that line to be able to find new points. So that relationship held true there as well. One other thing that's worth mentioning with that, if I reflect something across the line y equals x, if I reflect it across anything, it will always be the same shape. Now, that shape could be turned on its side in the process of doing that reflecting, but it will always be the same shape. And that's worth adding into your notes there. Because if I start with a parabola, the inverse is not going to be absolute value. If I start with a line, the inverse has to be a line. The inverse will not all of a sudden be a parabola. It has to be the same basic shape as the original. All right, moving on here, the domains and ranges are swapped. We saw that a little bit ago. The whole idea is because domain talks about x and y talks about y, and the inverse flips x and y. And finally, the notation and how we read that notation. Make sure that you understand what it means when we see that f to the negative 1 of x, and that we don't read it that way. We read it as the inverse of f of x. All right. Next up, we're going to do a little practice with the equation side of things. I'd like you please to find the inverse of each of these three equations on your own paper. Then to make sure you're on the right track, let's go back to the very first notes we took of the day. In order to find the inverse equation, step 1, swap x and y. So the first thing I want you to be writing in there, swap the x and y. If I can write it nicely. Then, step 2, solve for y. So make this into y equals from there. All right, so if I'm going to make this into y equals, that means I got to get rid of the 2, so I'm going to go ahead and divide both sides by 2. Now, when you do that, on the left side, there's a couple different ways you can write it. You can write it as x over 2 equals y. That's perfectly fine. You could also write it as 1/2 x equals y. Both of those are valid answers for this. And it's kind of a personal preference thing about which way you write it. Because the first one, it looks a little bit more succinct. The second one, it's a little bit more useful for graphing. But they do mean the same thing. So get used to being able to interchange those two. All right, for the second one, is the f of x throwing you off at all? Well, f of x works the same as what? Y. So first step that I would do in solving this one, finding the inverse, I'd write it as y equals x squared, and then go through my process as I normally would from there. All right, so if I change the f of x into y, our natural inclination then is to say, okay, well, then go ahead and start solving it. But what's wrong with this idea here? There's something wrong with what is up on the board. What is it? It's something rather important, and being able to recognize this is part of learning the depths of this thing. Yeah. I rewrote the f of x as y, but then we still have to make our first step is actually swapping x and y. And so really, I should have swapped x and y first. But this can happen, and I see it happen to people a lot. So what do you do if you forget? Well, you have two options. One, you can erase all of your work and go back and change it from the start. But when we swap the x and y, it actually doesn't change anything. So if you get to the end and you realize, oh, I forgot to switch them, you can actually do the switch at that point. And that's okay. It still works. It's not ideal, but I do want you aware that that can be done, especially as you get into the really long problems to find the inverse, because it could be really problematic to have to go back through all that work again, especially since you're doing the same thing basically. All right, now with this one though, there actually is one more step I'm going to go into now that I have this. I got the y equals, but my original was not y equals. My original was f of x equals. And so I'm going to give my answer using that function notation. How do I write the inverse in function notation? See if you remember, it's in your notes as well. That's where you write like that, f to the power of negative 1 of x. So this then is how our final answer should look.
What? Oh, does it have to be in that order? Can you like switch it?
Wait.
So it says negative?
Yeah, so I wrote it as the inverse of f of x equals. If you left the inverse of f of x on the right side, that's perfectly fine. Still means the exact same thing. Just when I'm tidying, I tend to put it first.
I'm kind of confused on the step that.
Right, and then for that last one, notice there's no f of x to worry about, so I can go straight to swapping the x and y. So x equals root y. How do I get rid of the square root? Square. We square both sides. So I'm going to do x squared, and I'm going to do the square root of y squared. So that gives me x squared equals y. And then that's our final equation for this one. But I want to forewarn you, because this is something we're going to be taking a much deeper look at tomorrow. There's actually going to be more to this answer as we start going further and further along. You're also going to see it a little bit on tonight's homework assignment. Y equals x squared is the inverse of this equation, but we're going to have to put in a little caveat with that. And it's going to be through that assignment and through looking at some of the graphs that we see what that caveat is. All right. Save that for tomorrow, though. For today, we got one more aspect we want to take a look at. Something we saw a little bit in the last class, hopefully on your homework. Switching between logarithmic and exponential forms. Please add this into your notes. And the reason why logarithms start coming up at this point is because what we'll actually find as we go forward is that a logarithm undoes an exponential. That is, it is its inverse. Those two equations are basically inverse equations of each other. The only thing that's not an inverse about it is swapping the x and y. All right, now with this in your notes, we're going to use this to figure out what each of these logarithms equal without even using a calculator. And it's all about being able to change the forms according to those notes that you took. So I'm going to walk you through number one. First of all, write down number one on your own paper. And the way that we deal with this is to figure out what the log equals, we can start by looking at it in terms of switching it into exponential form. So for number one, I'm going to take it from log form and put it into exponential form. You notice the very first thing I write in exponential form is the b. So looking at my original equation here in number one, what is playing the role of b in this equation? The 9, yeah. So I start by writing down 9. It's going to be 9 to the power of, in the original here, in the general equation, it's x. That's the number that it's set equal to in the log. You notice in this particular case, x is playing the role of x. So it actually is going to be 9 to the power of x.
Does that mean the next one's just going to be 5 to the power of x?
Equals what? It equals y. Notice where y comes from in the original. It's the big number that's in the log. It is 81. So in order to figure out the answer, we say 9 to the power of what equals 81. And that's something you can know off the top of your head. It's 2, because 9 squared equals 81, right? So, x equals 2. And the key to it is being able to think of it in terms of the exponential. So when I look at log base 9 of 81, what I'm really doing is I'm seeing 9 to the power of what is 81. Use that information now, figure out what 2 through 7 are. And of course, write each problem down along with the answers, so you have it as a future reference. All right, so number 2. When I look at that, what I'm really seeing is 5 to the power of what is 25. And so it's 2, because 5 squared is 25. Okay, 3. 7 to the power of what is 49? 2, yeah, because 7 squared is 49. Number 4, 3 to the power of what is 81? This one's not 2. Let's see here. 3 times 3 is 9. Times 3 is 27. Times 3 is 81. That was a total of 4 of them. So it's 4, yeah. 3 to the power of 4 is 81. Okay, number 5. 4 to the power of what is 64? It is 3, because 4 cubed is 64. Number 6. 5 to the power of what is 125? It is 3. And then number 7, the last one here, this is not one of the values I've asked you to memorize so far this year. All the others are ones you should have memorized. But we could still figure it out, even if it took a little guess and check. Like if I'm looking at this and I have no idea, I might guess something. It's like I might try 2 to the 10th. I get a number that's way too high there. Okay, so then I'd lower it. What about 2 to the 7th? Well, that's 128. That's too low. So then I go up. 2 to the 8th gives us 256. And so what you're doing here is a little different from some of the stuff you're doing on the assignments right now, but it's using the same skill. It's thinking about in terms of an exponential.